we will continue our discussion on extrema of functions. Fermat's theorem was so much powerful to determine where the extrema of, especially relative extrema of a function can occur. They can occur only at critical points. What is a critical point or a critical number? For a function f, a real number c in its domain is said to be a critical point, provided either f dash c is 0 or it does not exist. These are the way of how you are identifying critical numbers. Once you are getting critical numbers, from there we can systematically develop methods to find out the extrema. Fermat's theorem guarantees that extrema can occur only at these values. Moreover, there is a wonderful theorem which is usually called as extreme value theorem. But this can be applied in for the very nice functions, something like continuous function, which works on a nice domain. Nice domain, I mean, suppose f is a function which works on a closed bounded interval ab. That is, f is a continuous function defined from ab to r. Then extreme value theorem states that extrema, both extrema, absolute maximum as well as absolute minimum, should be taken inside the domain, which says, see, in your closed interval AB, if you have a continuous function on the real line, from this closed interval AB to the real line, then certainly you should be able to find some point C and D at which f of c is the absolute maximum as well as f of d is going to be the absolute minimum. Both these things are going to be attained. So remember, our function should be continuous. It should be defined on a closed bounded interval. But once you know this theorem, we can very systematically find out the extrema of a continuous function. So how to form that idea? So by the way, we will just state it for the completeness. So this is the extreme value theorem in full manner. Remember once again, f should be a continuous function. It should be defined on a closed bounded interval on AB. Then both absolute maximum as well as absolute minimum are guaranteed. It must take. Moreover, so how to find out in this case? What are the extrema of the functions like this? So strategy is clear. Just look at the critical points, compute the value of f, finally look at f of a and f of b also. Then absolute maximum as well as absolute minimum can be just taken from the data what you have given. So that methodology you can work out. So see, the idea is something like this. F is defined from AB to R. So our function may have very different behavior. It's not breaking it. That's true. That is the thing which is given, and it is a bounded interval. So our curve may be like anything. See, for example, it may be a continuous flow like this. In this case, if your function is looking like this, maybe this part a to b, it is defined. Then here, if you are searching for extreme values, maximum, absolute maximum as well as absolute minimum, then obviously it is going to occur at a as well as b from the figure. F at a is going to be the absolute minimum and f at b is going to be the absolute maximum. It may occur at the endpoints. So that also you have to count while looking at. So that is what I'm saying. At first, critical numbers you have to find out for the function the open interval AB. Then look for f of a and f of b. That is the second part you have to do. Then all this evaluation will help us to say what precisely are the extremum values and all. So this may take, the extreme values of function of the f, it may occur at the critical numbers, something like this. See, the figure may be, you can draw any figure like that. So if I'm having a figure like this, for example, something like this, if my curve is something like that, then what it happens is, see, from this, if the function is something like this, it is defined from a to b. So where this absolute maximum and minimum are going to occur, it is attaining. See, minimum is attained at here. I mean, it corresponding a C you will be getting. So C corresponding to that f of C is going to be the absolute minimum. Of course, it is going to be a critical point because f dash C is going to be 0 there. Now, there are other points here also, critical points in the interior part. But maybe according to this figure, absolute maximum is obtained at here. Corresponding to that, some D may be appearing here. So it may happen like this. Extreme values of f can occur. Critical numbers which are inside of this thing also may occur. Continuity is only guaranteed, looked at, and the bounded as well as closeness is also important for the domain. Even the function may look like this. See, sometimes a function may look like this, something like this. Here the function is continuous. So my domain is up from here to here, maybe marked as A to B. So what about here? This is a closed bounded interval. Function is continuous. No break is there. So what about the endpoints? A. The level of A is very small here. I mean, actually at A, it takes absolute minimum. At B, it takes absolute maximum also. If this node is somewhere here, which is actually in the same level, for example, it may take from here also. So these are the various ways of understanding the things where these extremas are going to occur. Anyway, fundamentally, we can use that guidelines determining the things and all. So formally, we will look at some examples which will help us. See, the first example is a polynomial. F of x is given to be 3x raised to 4 minus 4x cubed minus 8. The domain is given to be -1 to closed bounded interval. F is a polynomial, continuous everywhere, in particular in -1, 2 also. So how to find the extreme values? For that, the first step is about critical numbers. So the open interval -1, 2, you find out the critical numbers. Then check with -1 and 2 what happens, and all together will give you the final answer. So f dash x, it's a polynomial, so easy to find out the derivative. Rewriting in this fashion is also useful because equating to 0 will give something more. F dash itself is going to be continuous on -1, 2. Now f dash is going to be 0. Either this part is 0, that is 12 is not going to be 0. So x square is 0, that which means x is 0, or x equals x minus 1 is 0, that is x equals 1. So critical points are 0 and 1, right? So they lie in -1. You have to look at that. See, -1 is there, 2 is there. So somewhere in between you have 0 and 1, 2, like that. So 0 as well as 1, they are lying inside there. So in this -1, 2, we have 0 as well as 1. Now what you have to do? We don't know what happens at the endpoints also. So just list all these things. You look at 0, you look at 1, look at -1, look at 2, all the evaluations you make it and a list. That is enough. That is the third step. So corresponding to all these 4 values, 0 and value are the critical fellows. By f dash is going to be given to be 0. Just evaluate f value at each of these points using the function rule. F is given to be using this rule. So just find out all. F at -1 means 3 into -1 to the power 4, etc., etc. You have to put it, and we will get the evaluation as -1. Similarly, you find out 0, you will get minus x equals 0, x equals 1, x equals 2. So this will be the listing. Once you are verifying this from this list, it is clear. I mean, see, the large maximum value is going to be 8 and the minimum value is going to be -9. So maximum, absolute maximum is going to occur corresponding to the point 2, and absolute minimum, that is going to be occurring at 1. This is the full way of finding out all these extremum values. So first determine the open interval, the critical points, work out with the evaluations of f of that along with the endpoints, then list it. From that you can actually determine where these extrema are occurring and all. So maybe make it more clear. One more example. We'll write it down. F of x, it's a trigonometric function combination with a polynomial one. So f of x, if I'm writing it as 2 cos x minus x. See, this x is a polynomial, 2 cos x is a trigonometric function. So both are continuous and all such things are even differentiable, everything is there. So just this combination is going to be a continuous function. It is continuous everywhere. So we are asked to look at 0 to 2 pi. So that should be important, which interval you are. So we are working with a closed bounded interval 0 to 2 pi. So here a little bit more work you have to do. F dash x, it is easy to find. It is minus 2 sin x minus 1. Then look at the open interval 0 to 2 pi. Just to find out f dash x equals 0. The corresponding points for f dash equals 0 for x will give the critical numbers. So this gives you minus 2 sin x minus 1 is 0, which ideally gives sin x is minus half. Now you have to look at for what, see, sin x you have to get minus half. But you should remember that you should work inside 0 to 2 pi. So remembering that also, evaluations of such things if you are looking at, you can verify that x is either 7 pi by 6 or 11 pi by 6. Because they should lie in 0 to 2 pi. So many other values you will be getting, but you should be strictly in between that. So in between 0 and 2 pi, these 2 points are going to be the, which gives actually f dash is 0. So critical points from that side is over. Now at the endpoints, 0 and 2 pi also you have to look at. So as a tabulated way, you can calculate 0 is the one endpoint, 2 pi is another endpoint. Just give the evaluations on this f of x for the corresponding x values. Put x equals 0, find out the final evaluation as 2. 2 pi also will give something like this. Also, you have to put all these values and roughly calculate all these evaluations. From these evaluations, just look at which is the maximum as which is the minimum. Then immediately you can find out the extremum values. So this is a general strategy, and so optimizing techniques can be developed using that. So it can be used as an optimization problem in many ways. I mean, either the maximum, absolute minimum. So some modeling is taken out, as that modeling will be a mathematical equation which will be continuous, and appropriate bounded interval can be find it out. So just apply this to get the optimum values. That is optimal solution, maximum as well as minimum. So that is how this is helping us in the optimization problems. So this kind of techniques one can develop. So this extreme values, once you are able to do more strategically, I mean calculus ways we can do once more theory is going to be developed. So we'll slowly pass over to the next session, which is also giving right hints to attack more general calculus setup, which is very celebrated one, which is called the Rolle's theorem. So we'll just look at Rolle's theorem now, which is a little bit familiar with us. So Rolle's theorem, what it says, see, as we have mentioned already, while in the last discussion, our function was continuous, which was defined in a nice domain, closed in and bounded interval, and it was a continuous one. So something we have already observed. So continuity on a closed bounded interval, which is a very nice phenomena for nice functions, getting functions. So that is one of the ingredient for the Rolle's theorem. Remember that Rolle's theorem, in its full statement, what is going to happen is you need a continuous function again on a closed bounded interval. A little bit more we are expecting smoothness, I mean differentiability also. So differentiability of the function we are asking for the open interval AB. We are not looking at endpoints. Moreover, at the endpoints, I mean f at A and f at B, you can evaluate. And if they are agreeing, I mean f of A equals f of B, then Rolle's theorem is guaranteeing one more thing. That is, actually you can find out some point from A to B, I mean open interval AB, for which f dash C is going to be 0. So f dash is going to be 0 at some point, the interior part or inside part will actually gives us critical points and extreme points way, the methodology how to go for extreme points. So Rolle's theorem is highly influential, helpful for us in this strategy. So, but Rolle's theorem can be applied in this situation. You take a closed bounded interval, a continuous function is defined, and the open interval AB, if you have differentiability, f dash is existing, and in addition to that, f at A should be same as that of f of B, then in between A and B, in the open interval A and B, some C can be found out for which f dash C is good. A statement is f is continuous at a closed interval AB and differentiable on AB, open interval AB, and this condition you remember, then it guarantees at least one number f dash C exists. So as I mentioned before, if it is a constant function, the first figure will guarantee that every point in between the first figure from A to B, every point is going to give such conditions for you. You are not worrying about A and B, all other points here also. But in the second situation, which is not a constant function, but still what happens is you'll be able to find out so many C's, C1 and C2, which is suitable for Rolle's theorem and all. So how we quickly look through the proof, how the proofs are going to happen. See, obviously you look at the first figure, whenever it's a constant function, f of x is going to be d for this is what is f of x. This is going to be a constant function. It is always d throughout AB. In that case, what happens? You find out f dash x. A constant means derivative is going to be 0 everywhere. So all the points, obviously, C, any point in C, A to B will do that. F dash C is going to be 0. So theorem is proved. So second case is this one. A figure may be like that. What it says? It says that f of x is not a constant one. F of x is not equal to d. That is what it says. So it may figure like this. So our f of x is not going to be d for at least one x in AB. That is what it says. So if you are looking some point, at least some points in AB for which f of x is not exactly equal to d. So in this case, you should be able to find something. So that is the non-trivial part. So how will you find a C suitably for us to make it? So see, from the figure we will get the hints what you have to do. See, f of x is not equal to d. F of x is a real number. So trichotomy we know. A real number, A and P and Q are two real numbers. Either P equals Q or P is less than Q or P is greater than Q. Just depend on that. Then you can easily go for the thing. So in this case, suppose f of x is not equal to d. So if f of x is greater than d, or what may happen, f of x is less than d. One of these cases may occur. So suppose that f of x is greater than d. Now remember, f is a continuous function on a closed bounded interval AB. So you can apply extreme value theorem. So it attains an absolute maximum at some point C in AB. That is how you are applying. C is available inside AB. So this extreme value theorem will give an choice for absolute maximum. But the number C cannot be an endpoint because f of A, if you are looking at f of A, which is given to be f of B, but f of A is f of B, which is going to be D. And we have already assumed that f of x is greater than d. So it cannot take like that. So our C must be inside open interval AB. That is how the proof goes. Very simple proof, but very genuinely we can argue like this using the extreme value theorem. Now f is differentiable on AB, open interval AB. So f dash C exists. So f dash C exists, it is guaranteed. From that, Fermat's theorem you apply. So f dash C must be 0. So entire thing is over. So once f of x is greater than d, you can work like this. Very similar proof one can give, and you can argue in the case that f of x is less than d also. So the Rolle's theorem, the content of the Rolle theorem you should remember well. F should be a continuous function. It should be defined on a closed bounded interval. Secondly, On the open interval AB, it should be differentiable. Then some C in the open interval AB is guaranteed, for which f dash C is going to take 0. That is what it is given. So remember the statement as well as the content. So let us work with some example, very simple example. F of x equals x cubed minus x. We are working on -1 to +1. It's a closed bounded interval. It's a polynomial again. So everywhere it is going to be continuous as well as differentiable throughout the real line. Polynomial functions are like that. Now conditions are satisfied. So the first part is show that f satisfies the hypothesis of Rolle's theorem. That is clear because polynomial functions are like that. Moreover, what it says is the f at -1 is what? F at -1 as well as f at 1 also you can look at. F at -1 is 0, f at 1 is 0. So all the hypotheses, there are three conditions. Remember that f should be continuous in the closed bounded interval and the open interval is differentiable. In addition to that, f of A is same as f of B. That you should remember. That is, see, you are having the same level at the endpoints. That is more important in this level. Otherwise, you can't expect the things, right? Geometrically, whenever you are looking at, and the curve is something like that from left, and up and down, and this certainly is guaranteed once you are assuming f of A and f of B are same, right? So that is an important thing. Later we can tilt it a little bit different manner, but still. So this guarantees the thing. So you have to, all the hypotheses if you are checking, continuity you have to check it throughout the closed interval, bounded interval, differentiability in the open interval. Here it is -1, 1. And obviously at the endpoints they should agree. So all the hypotheses are satisfied, conditions are well. Now what you need, you have to find out some C in this interval. So what is the strategy for f dash C equals 0 such C's? F dash you find it out, equate it to 0. So which is a quadratic in C and it will give plus or minus square root of 3 by 3. So these 2 points are lying in here. That you have to check it, which points are inside, then that gives you f dash C is 0, and that is how we are verifying Rolle's theorem in different problems. Obviously, there is, as I mentioned, a slight variation of this thing. In fact, not slight variation, because once Rolle's theorem is there, a special case you can give it. In fact, you can say that a very special case. The whole Rolle's theorem is going to be a very special case of the very general setup that we are trying to say, which is called as the mean value theorem. So as I mentioned earlier, see, the whole content of Rolle's theorem, geometrically whole things are very much evident. Once you are having a closed bounded interval, you have functions like this. Continuity of f is here. Differentiability is guaranteed in the open interval. Then at least existence of some C where this fellow is, the function should be somewhere here. It has to come like this, right? F of A should be here, f of B also should be here. It's same level. Then only you can guarantee something will happen, right? So these three conditions, f at A, f at B, they are in the same level. So either he has to rise and you have to come down. If it is going down, then you have to go up and you have to stabilize. So this leveling, f of A and f of B, they are equal, which gives that up and down strategy as a down and up strategy. So certainly there should be a stabilization, which makes the passing through that tangential thing is towards horizontal x-axis. So that idea you can manipulate a little bit more. See, whenever you are having a curve like this, having the same level, at here if I am looking for, I will get a critical point here corresponding to C here. Now suppose I am tilting a little bit, still I can talk about a little bit more. See, suppose I have a curve like this. So here maybe A, this may be my B, this I will refigure, my figure may be like this. So maybe I start with A and I will end up with B. This is my closed bounded interval. My function is something like this. So at this point, for example, see, this is my f of a point, this is my f of b point. So here I can't expect that f dash is 0 or somewhere sometimes, right? But at least see, even if I am looking f of a and f of b, this point corresponding to a f of a, this fellow is b f of b, right? So I can even think about the code of from P to Q, if I'm marking P and Q here. So certainly with the condition, the hypothesis, at least first and second, that is f is a continuous function on AB, differentiable on open interval, then from the figure what is going to happen is the following. See, at this point I mean the curve, this chord is having, see, this chord means the line through PQ I am looking at, and the line segment, that is chord. So this line segment has a tangent, sorry, the slope. This slope is going to be same as somewhere here, right? A tilted way. If you can think from the Rolle's theorem, you can think about a tilted way, but this is more general. Now, if you are looking at this line, what I have drawn here is a tangent at, see, this point I may mark it C. C corresponds to these points. So this point, precisely speaking, it is CF of C. So if I am looking at the tangent at C, which means CF of C point, this is the tangent at C, corresponding to the point C. See, this tangent as well as this chord, they are having the same slope, right? So the tangent, the chord actually is, what is the slope of this fellow? I mean this PQ. Y difference, that is f of b minus f of a divided by b minus a. That is the slope of this chord. And the tangent, it is differentiable if it is guaranteed, then at C this says that that is the f dash at C. So these should be equal. That is what the more general setup for this. So what are all the ingredients what we need, what you are trying to talk about? So f should be a continuous function on a closed bounded interval. Moreover, it is also differentiable on open interval AB. We are not assuming that f of a and f of b are same, but in this general setup what you are going to get, certainly you will be getting a point C in our open interval, for which f dash at C is going to be same as f of b minus f of a divided by b minus a. This is what, or precisely, the known as the mean value theorem, which is a very nice generalization of Rolle's theorem. So once you are having this, obviously you will get Rolle's theorem as a byproduct, because see, this is the, see, the code what you have selected is having a general one here. You make it parallel to the x-axis, because f at a and f at b are same, means same. This will be pushing down from the right, which means it will be something like this. So and up and down like that. So these two fellows are going to be equal. So that's as a special case, you will get f dash. Things are going to be like that, nothing more than that. So it's a very special case of that thing. Rolle's theorem is a very special case of that thing. So what about the proof of these things? So okay, formally we will state it. So this is the whole scenery of mean value theorem, very precise way of talking about continuity and differentiability appropriate hypothesis. Then after see what it happens is given. So for the proof, the only thing what you should remember is see, you should find out this equation in the sense that the slope already we have seen, that is of the chord is going to be f of b minus f of a by b minus a at the point. So what you have to do is just relate the first find out the equation of the secant, basically the secant line, you can say about that. The secant chord is a general for generally reserved for circles, but you can use a secant line. And there, so the secant is the correct word to use. So secant line, if you are looking at the find out the equation of the secant line. So what you are going to get the equation of the secant line as y minus f of b. I mean, see what is happening is p correspond to a f of a, q correspond to b f of b. That is the point wise if you are looking at. So these 2 points joining together, the secant line equation is given by y minus this y1 is going to be the f of b, the slope of the part, f of b minus f of a by b minus a times x minus b. So rewrite it, y is going to be in this type. The equation of the secant line passing through this p and q will be y equals f of b plus f of b minus f of a divided by b minus a into x minus b. Now, just remember what you have done on the how to apply the Rolle's theorem in the appropriate way. So just make a manipulation on this function. Just make it so that the whole thing is tilting down, rotating down. So consider a function from this. That is what is called dx. Dx, how will you define? F of x value minus the already find out the part of what you had observed. Just remember that. Before that, it was the secant line has the right hand side part like this. Y is becoming like that. That is the f value. So that f value is nullified with the f of x values. This is the value given in the previous setup. That is the y values are given for the function. Now, just use that and manufacture a new function d. So d of x is f of x minus this. So obviously what the things are going to happen is clear. D, if you are looking at, what's the speciality of d of x? F of x minus this fellow. Obviously one can see that is a continuous function. Oh, can you say that? See, it's a constant fellow. This part is x minus b part, that is a polynomial part. His f of x is also continuous. So whole combination is going to be a continuous function on the closed bounded interval ab. Differentiability on the open interval is also like that. Now, in addition to that, what is going to happen newly? Just to find out the n values, d at a. D at a, if you are looking at, just push that f of a you put here. Here also a will come. So altogether you can simply say that this becomes 0. Sorry, this becomes 0. Moreover, this is also same as that of d of b. This is the whole thing what you heard. See, that is expected because see, this is the equation of the secant line part. Y values are given like that. Y values for the function is f of x. You are just making it nullifying. That basically that what you are giving the distance, vertical distance between f and the secant line. You wanted to make it something. That's all. So you just make these appropriate changes. This function d of x actually at a and at b we are going to be giving as 0. So they are agreeing with the same value. So what you need more? D is a continuous function on a closed bounded interval, differentiable on the open interval. They are agreeing at the endpoints. So some c should exist for which this f dash c is going to be like that. See, this d dash should be like that. So how to apply that? D, so there should be some point c in our domain, open interval ab, such that d dash of c, I mean d dash I mean d prime of c, or you can say that is going to be 0. But what is d prime? D prime is f prime. See, just look at d. So you will have f dash part here. This will go off. On this side is a constant. So this is again a linear one. On 1 x minus b, just 1 will be the derivative. So derivative is simply this. So derivative d dash at x is this one. So there should be some point c because of Rolle's theorem for which f dash c minus f of b minus f of a by b minus a should be 0. Rewrite it. You will simply get f dash c is equal to f of b minus f of a by b minus a. So this is the whole proof of the mean value theorem, more generalized Rolle's theorem, you can say. So remember all the hypotheses once again. F should be continuous on the closed bounded interval, differentiable on AB, open interval. Some C existence is guaranteed by the mean value theorem, for which f dash C is going to be f of B minus f of A by B minus C. Very similar way of what you have done on the problems there, we can work on here also. We can find out in a similar way also. So let us discuss it later. Okay.